Sorry for the delay. Welcome to the lesson finishing intermolecular forces. We left off on, I don't know what day that was at this point, Thursday last week, talking about van der Waals forces. And we said that van der Waals forces are forces between nonpolar molecules. Okay, and they occur, and they're very, very weak. And the reason why they're very, very weak is that if you remember, nonpolar molecules do not have partial charges. So in most cases, nonpolar molecules don't attract each other. We discussed on Thursday that every once in a while what happens, okay, is that electrons run into each other in a nonpolar molecule. And what they do is they create a temporary negative charge where the electrons are like all clunked together, and a temporary positive charge where there's no electrons, or the electrons are devoid, is the way it's usually said. And now, for a short period of time, or a temporary period of time, this nonpolar molecule does have partial charges, which can be attracted to other molecules. But again, this doesn't happen that often, so therefore the forces of attraction are weak. Now, I left off with you with a question at the end of the class, and I said, like, well, if you could get this question right, you're a genius. And the question was, what type of molecules have stronger van der Waals forces? And so I'm going to tell you now, unfortunately, because I can't write on the PowerPoint, so you're going to have to write down what I say, and actually this is an important skill for college. So, and when we do, if you do AP Chem, you're going to have to do that all the time, is instead of writing down what I write on the board, write down what I say. So in some ways, this is a skill to learn. So nonpolar molecules that have strong van der Waals forces are big. So bigger molecules have stronger van der Waals forces. And the question is why? Well, bigger molecules generally have more electrons. Or not, they usually always do. And therefore, since there's more electrons, they're more likely to run into each other. And if they're more likely to run into each other, you're more likely to get a temporary negative charge that something can be attracted to. So if you need to replay that to write it down, you should. But larger molecules have stronger van der Waals forces because electrons are, when there's more electrons, they're more likely to run into each other and create a temporary negative charge that can attract something else. So, we've learned all the four forces. Ion-ion forces right here. They're between ionic compounds. Hydrogen bonding is between polar compounds that have H and F over N. Dipole-dipole forces are between molecules that are polar that don't hydrogen bond. And then van der Waals forces are between nonpolar molecules. Remember, van der Waals forces are also called London dispersion forces. On the PowerPoint slide that you're looking at now, the forces are listed from the strongest to the weakest. So ion forces are the strongest, and van der Waals forces are the weakest. To remember the strength of the forces, I have come up with a sentence. I hate dirty, and whatever V word you'd like to choose. I personally don't like dirty vacuums, because then the dust gets everywhere when you gotta clean it, and there's cat fur in it. But I for ion forces, which are the strongest. H for hydrogen bonding, for hate. Dipole for dirty, and then vacuums for van der Waals forces. And that helps you remember the order of the forces from strongest to weakest. So what we're going to talk about now is how intermolecular forces affect the properties of molecules. And the controlling idea, which is on the slide as you see right now, is that the stronger the intermolecular force, okay, the harder it is to pull the molecules apart, okay, and therefore the higher the melting and boiling point of that compound. Remember, to melt or boil something, what you have to do is you have to move the particles further apart or increase the potential energy. And if molecules are really, really attracted to each other because they have a strong intermolecular force, it's really, really, really hard to pull them apart, and it's going to take more energy to do so. Therefore, they're going to have a higher melting and boiling point. So these are general conclusions that are sort of like rules of thumb, and like I said, and I'm sorry again, there are lots of exceptions to these rules. But for small molecules, anything that has ion-ion forces is a solid. Actually, there's no exception to that. All molecules that have ion-ion forces are solids. And then small molecules that have van der Waals forces tend to be gases, except for really, really, really large nonpolar molecules. For example, sand is a nonpolar molecule, and it is actually a solid. But most small molecules that are nonpolar and have the van der Waals force tend to be gases because they have weak forces of attraction. and therefore the molecules are really far apart from each other. Now, methane, if you drew methane, and let me try to draw methane with the pen, because I kind of do need to draw it for this. Let me see. Where are you, pen? There you are. So methane looks like this, a tetrahedral molecule, and it's going to be awful. I apologize, because I'm writing with the mouse, which is very, very difficult. Methane is a tetrahedral molecule. Those are hydrogens, by the way. I'm sorry for the lack of ability to write H. And that's a non-polar molecule. Okay? And then this is water. Water's bent. That's O. So I apologize. And that's a lone pair. Lone pair. Lone pair. Lone pair. Lone pair. And then we need our H's. Probably should have gotten a picture of this, but oh well. That is water. Now, you need to write down everything that I say here. So if you need to stop the video and replay it, you need to do that. The question is, why is this a gas? So this is what cows fart and what we fart sometimes, and this is water. Obviously, we all know what water is. Why is this a gas and this a liquid? So I'm going to go through the whole sort of explanation. You need to write down the entire thing. So this is nonpolar because it's symmetrical. As a result, it has van der Waals forces, which are weak. Because the van der Waals forces are weak between particles of methane, the molecules are very, very far apart. And when molecules are very, very far apart, things are gases. Whereas this, which is polar, okay, and has partial charges, it has a strong intermolecular force between its molecules of hydrogen bonding. Because of that, the molecules of water are closer together, and that makes water a liquid. Okay? Make sure you've written that down. And if you need to replay it, replay it. Alright, this is the last slide, and then there are some questions that you can do, which will give you time in class to do. You need to listen and fill out this chart. Okay? In this box here. Ion forces are between ionic compounds. They are the strongest, okay, force. And things that have ion forces tend to be solids. Hydrogen bonding is between polar compounds that have hydrogen and, so plus, either F, O, or N. They don't have to have all three. They need to have one of these three, and they have to have hydrogen, and they need to be polar. This is the second strongest, and you can't really tell the phase of matter. It's like some of them are gases, some of them are solids. There's not like sort of a rule that works here. That's the same thing for dipole-dipole, which you're going to see in a second. Dipole-dipole is for polar things that don't hydrogen bond, so that don't have H and one of F or N. They're the third strongest, and again, you can't really tell the phase that well. And then van der Waals forces are between non-polar molecules. They're the weakest, and things, not all things, there's lots of exceptions, but small non-polar molecules that have van der Waals tend to be gases. Alright, so if you're doing this video now, I want you to do the practice questions. But thanks for watching. Have a good day.